Long before it became home to Cone Drive, the John Parsons Building played a vital role in American manufacturing. From its early industrial use to supporting the war effort during World War II, when bombs were wrapped within these very walls. This building has seen over a century of hard work, innovation, and resilience. In 1950, Cone Drive moved in and became part of that legacy, one rooted in craftsmanship and commitment that continues to this day. The following archival footage offers a rare behind-the-scenes look at the bomb wrapping operations that took place here during World War II. A powerful reminder of the building's history and the people who shaped it.
Brings many changes in the thinking and actions of a nation. To an unperturbed America, it brought changes that were swift and sudden. Changes in her men, in their habits, and in their lives. New type guns and tanks were developed in a hurry. New bombs for use with new high-speed airplanes were developed overnight. This meant changes in industry and in the plants that produce the weapons and the machines of war. Overnight, the song of steel rang with a rising tempo in countless shops. The miracle of manufacture wrote a new chapter in the saga of American industry. Growth, expansion, development were typical of the time, not only among the mammoth industrial leaders, but in the smaller companies as well. No equipment was available to manufacture bombs. Each company had to work out their own methods. How industry met these problems can well be illustrated by taking the case of one company. Its story offers a sound example of American ingenuity and know-how. Actually, the story should begin early in 1942, in the heart of industrial America, Detroit, Michigan. Here was the enemy's #1 target, if they could reach it. Here also, as elsewhere, construction steel was very tough to get, and manpower was at a premium. The Parsons Company met these problems, first by purchasing this building from a scrap dealer. Not much to look at, it's true, but it had a sturdy tile roof and good steel work in it. Then American ingenuity got busy and solved the remaining problems of manpower and safety by rebuilding the old plant more than 200 miles away in Traverse City, Michigan. Here indeed was a case of the mountain going to Mohammed. This new plant grew from the efforts of just 4 men assigned to build and run it. Erected in the heart of Michigan's vacation land, all of its workers were drawn from the surrounding peaceful countryside for one purpose: to build bombs. Under wartime pressure, steel tubes and other bomb-making materials were soon rolling up to the back door. Parsons' pre-war experience with stamping and cold-forming processes dictated the fundamental principles of the new Parsons process. For example, these bars of steel are used in making fragmentation bombs. The bars are 58 feet in length, too long for standard railroad cars to handle. The bars are unloaded by a special locomotive crane. This crane lowers them to the bar loading rack. Here the cables that carry them to the rack are unhooked, and later the steel bands that bind them together are removed. Once the bars are separated, they are placed individually on a special motor-driven conveyor. This conveyor carries them inside the building. They continue traveling along the conveyor track to the bar furnace. For each bar of steel that goes into the making of a fragmentation bomb, a steel tube is likewise used. The tubes are also carried into the plant by a motor-driven conveyor. The steel bar is used to form the exterior of the bomb. The steel tube forms the center section of the bomb casing. So the initial objective in fragmentation bomb manufacture is to wrap the 1-inch steel bar around the metal tube. To accomplish this, the bars are first fed by the conveyor at the left into an oil-fired furnace. The furnace heats the bars to a temperature of 1600 degrees. Normally, this takes about 30 minutes. The furnace itself was designed by the Parsons Company. It is 66 feet long. 2 tanks, each holding 2 full carloads of oil, supply the fuel. One unusual feature about the furnace is that the bars are fed continuously across the bed. This is accomplished by means of hydraulic cylinders. As a result, the bars drop out of an open side of the furnace instead of being removed from one end. This design increases production because it allows heated bars to be drawn to coiling machines at both ends of the furnace instead of just one. The basic design of the coiling machines is the same as that used for making knee-action springs for automobiles. However, the Parsons Company adapted the design to their own requirements after obtaining the rights to use it. This machine has the capacity to coil a 1-inch bar cold. Notice how evenly and tightly the coils are wound at cherry red heat. After the bars are coiled, they are cooled in a quench machine that sprays them with cold water. The coils are cooled so that they may be handled immediately through the next operation. As the coils reach the rear of the quench machine, they trip an electric switch. This automatically moves the coils forward through the spray. The coils emerge from the spray completely cooled and ready for the next step. This consists of squaring the ends of the coils. The ends are squared by using an end-burning fixture that the Parsons Company developed. Not only does the end-burning fixture cut production time, but it has produced a substantial saving in metal tubing over other methods. This method is simplicity itself. While the coil revolves, 2 oxyacetylene torches cut away the excess bar metal. Note that the cutting torches trim only the bar and not the tube. After the bomb ends are square, the coil is removed from the fixture. The coil then travels along the conveyor to a point where the ends are tack welded. The coil is then ready for the tapering operation. The tapering is done by any one of a battery of 6 identical machines. The rough bombs are loaded into the machines hydraulically, using equipment developed by Parsons to fit this particular operation. The tapering machines themselves are unique in that the work is chucked in the middle. This allows both ends of the coil to be tapered at once, cutting tapering time in half. The purpose of this tapering is to remove excess metal from the ends of the bomb. Then the remaining metal will flow properly during forging. All feeds, both cross and longitudinal, are accomplished by means of hydraulic cylinders. The main thought behind the design of these lathes is to get the bombs in and out as quickly as possible to reduce loading time. Note that when the operation is completed, hydraulic pressure forcing in a new bomb also serves to force out the bomb that has just been machined. It is then ready for the forging furnace. At the Parsons plant, 2 furnaces were installed for the forging of fragmentation bombs. The flame shooting out of the stacks of the furnace indicate how the furnaces are being forced to heat as many bombs as possible. In one, the tail is forged, and then in the other, the nose. Both furnaces are 20 feet long, are oil-fired, and will heat the ends of the bombs to a temperature of 2,200 degrees. The body of the bomb must, of course, remain cold to prevent buckling under the heavy blows of the press. To accomplish this result, each furnace incorporates a very unusual feature. Specially made refractories, which actually serve as the hearth of each furnace, are used to prevent heat from traveling down the body of the bomb. The refractories are automatically picked up by an overhead conveyor system after they go through the furnace. The overhead conveyors carry the refractories over the top of the furnace. Meanwhile, the bombs reach the furnace on another conveyor system. Here they are removed from the conveyor. Then they are placed on special trucks. The trucks carry them on rails through the furnace. When a truck is properly located, a refractory is lowered over the bomb by the conveyor. Only the tail of the bomb is thus subjected to the intense furnace heat. The bombs move through the furnace in approximately 5 minutes. About 20 bombs travel through the furnace at the same time. So that proper heating may be accomplished at this speed, the furnaces are carried at 2,800 degrees. When the bomb emerges from the furnace, the heated portion is at white heat, ready for the forge press. The refractory is automatically removed from the bomb by the overhead conveyor system. The bomb and truck are drawn along the track directly into the forging press. The bomb tail is forged in the cone-shaped die in just 5 strokes by pressures in excess of 12,000 pounds per square inch. When the bomb is removed from the forge, the tail is forged to finished contour. However, it is still red hot and must be cooled. For this reason, the bomb is hoisted from its truck and placed in another quench machine. This spray quench operation is repeated every time the bomb coil is heated in a furnace. The spray method is used in preference to immersion because it simplifies handling of the bombs. After the bomb has been cooled so that the tail will not be affected by the nose forging operation, it moves to the nose forging furnace. Here, the bomb is lifted from the conveyor. Then it is lowered tail first into a suitably shaped forging truck. The loaded truck then moves down the track to the furnace. Before the truck is pushed into the furnace, a refractory is first placed over the bomb so that only the nose will be heated. The heating operation is identical for both furnaces. The refractories serve as the hearth. They protect the body of each bomb from the intense heat as it passes through the furnace. The presses which forge the nose and tail of the bomb are the crane type, without gearing or clutch. Each press has a 4-inch stroke, runs at 100 strokes per minute, and is driven by two 40-horsepower motors. Each has a rated capacity of 450 tons and weighs 40 tons. The presses stand 22 feet high, 15 feet above the floor, and 7 feet below. The Parsons Company designed and built its own presses to save time and get the job started at the earliest possible moment without interfering with the serious demands for production machinery. One of the outstanding features of this press is that the bed rises hydraulically to feed the bomb into the die. The speed at which the bed lifts is decreased as more pressure is applied to form the bomb. The amount of lift varies from 2 inches on the first stroke to about 1/4 inch on the fifth or final stroke. This allows the metal to flow quickly at first, then slower as it cools off. While this is the first time that the Parsons Company has done hot work, since its pre-war experience was limited to small cold metal stampings, its resourcefulness in designing such presses well illustrates its ability to progress with the times and meet new requirements. In fact, these presses proved so successful that similar ones were built for other bomb manufacturers. It is also a tribute to the small businessman that the only outside people who had any part in designing or building such equipment were the little producers. There was no drain whatever on national resources. It was a case of making the most of what was available in the way of material, and a lot of it was scrap. But it did produce results, and that was what Uncle Sam wanted, even on the smallest operations, for they, too, might be important. Here, for example, is an important operation in which suspension lugs are tack welded to the bomb after it comes from the final quench machine. After the tack welding is completed, the lugs are given a full weld to fasten them securely to the bomb coil. and then the nose adapter is added to the bomb. First, the adapter is placed in an air-operated fixture. This fixture accurately positions the adapter in the bomb. While the adapter is held in place, it is firmly welded to the nose. The next step is to clean the bomb thoroughly. In the cleaning operation, a conveyor hanger is first inserted in the nose of the bomb. Then the bomb is lifted with a hoist. By this means, it is removed to a shot blast machine. Here, the bomb is placed in one of the 4 compartments of the machine. To clean the exterior, shot is driven against the coils by a rotoblast. Air, supplied by 2 700 cubic feet compressors at a pressure of 100 pounds per square inch, assists in cleaning the bomb interior. In this 4-station machine, the blasts clean a bomb in 30 seconds. After the bomb is thoroughly cleaned, it is stamped with a rotary stamp driven by an electric hammer. This is a much faster operation than hand stamping. By the way, notice this special roller conveyor. Not only does it carry the bombs along, but it allows them to be rotated at will with minimum effort. The first of a series of many tests is then performed. To test the strength of the suspension lug weld, air-operated fixtures are used. The fixture at the right tests the 2 lugs by which the bomb is suspended in American planes. The other fixture tests the single lug used to suspend bombs in British planes. These tests make sure that the lugs will withstand the terrific strain of dive bombing. After the tail adapter has been added and welding completed, the bomb is ready for the painting operation. It is hoisted to an overhead conveyor upon which it remains until final assembly. Prior to painting, the bomb passes through a heating unit. Here it is heated just enough to assure rapid and complete drying of the paint. After emerging from the heating unit, the bombs travel along the conveyor to the paint machine. This paint machine was designed by the Parsons Company to do a special job, and it is one of the most interesting of the production line operations. As the bomb enters the paint machine, contact is made with a trigger that operates a moving belt. This trigger strikes the bomb at about the center of the coil. The moving belt causes the suspended bomb to rotate in its swivel. Next, 2 spray guns rise at the left to paint the outside of the bomb completely with a red oxide primer coat. A 3rd spray gun enters the tail of the bomb at the bottom of the machine and sprays the inside thoroughly with an acid-proof coat of black. This occurs at the same time the outside is being sprayed with oxide primer. The bomb is painted without interrupting the progress of the conveyor. During this spraying operation, the bomb moves approximately 20 inches. Experience gained in producing other ordnance equipment was used in designing this paint machine. Upon leaving the paint machine, the bombs travel along the overhead conveyor to receive another series of tests to make sure they are leak-proof. Following these tests, they move toward the final assembly line. Here, the bombs are removed from the conveyor and prepared for shipment. First, shipping bands are placed around each bomb to protect it during movement. These will remain on the bomb until it is ready for loading in an airplane. Nose and tail threads are carefully inspected before plugs are installed at each end. Other protective parts are added. And finally, the insignia of the Ordnance Department is stamped on each bomb to show that it is satisfactory and that it has met rigid government specifications. And so the weapons of war roll on their way, from the heart of a traditionally tranquil countryside to a loading plant, and then to the blazing battlefields of the world. Yes, here is a story of change, a fitting example of American adaptability to the times. Bombs for America today, forerunner of the pattern for peace, the design for tomorrow.